Welcome to today's Alde webinar, Don't Be Afraid of UVM, or UVM for Hardware Designers. I'm your host, Christina Toole. Thank you for joining us. Alde is an industry-leading EDA firm delivering innovative design creation, simulation, and verification solutions. This webinar is geared toward busy hardware designers that have little time for experimentation with new methodologies. Today we will concentrate on details such as connecting UVM testbench to your design. We will also review SystemVerilog interfaces with special attention paid to virtual interfaces, sequences, and other data items, as well as the role of monitors and scoreboards in analysis of results. Should you have questions during the webinar, we invite you to use the questions panel to the right of the screen. And we'd also like to let you know to expect emailed instructions to download a recording of today's presentation. Your presenter today is Jerry Kaczynski, Alde Research Engineer. Welcome, Jerry.
Thank you, Christina. Let's see if we can proceed to our agenda. As everybody should see, it's a relatively short one. We'll have brief introduction, explanation of some very basic ideas, then the core of the presentation, actual description of UVM, and again, very brief conclusion. So let's proceed to our introduction. First important question, what is UVM? UVM, which of course expands to Universal Verification Methodology, is just a library of SystemVerilog classes and some other utilities, which is supposed to simplify creation of advanced reusable verification environments. UVM requires at least basic understanding of two programming concepts. The first one is object-oriented programming, or OOP, and the other is transaction-level modeling, or TLM. The better your understanding of those two concepts, the more you can squeeze from UVM. If you know nothing about them, then it will be really hard to proceed. Everybody who attends probably has seen our suggestion that if you do not feel comfortable in those two areas, you are always welcome to visit our previous webinars dealing specifically with OOP and TLM. And as the subtitle of our webinar states, we are trying to present UVM from hardware designer's perspective. So let's see if and how typical hardware designer can deal with UVM. So typical hardware designer can quickly learn enough use UVM to first use verification IP written by others and work with verification engineers on creation of some new test benches. Of course, creating advanced UVM test benches or creating verification IP in UVM requires slightly more knowledge and practice. Another important question, who needs UVM? First official statement is that UVM works best in case of bus-based high-traffic system-level designs. And it is also most efficient when verification procedures require randomization and or functional coverage. If you are dealing with other designs, so if they are small, do not require randomization and coverage, of course you can still use UVM, but probably it will not be the best solution. Please remember that UVM uses mainly black box verification approach, so it does not make assumption or does not check any internals of your design under test. So it should work with designs written in any language, of course, provided that the simulator that you are using supports both SystemVerilog and the language in which design is described. Okay, so now let's signal some very basic ideas that must be clear before we proceed to a detailed description of UVM. First of them is object-oriented programming. Object-oriented programming always involves classes, so of course we have sample class written in SystemVerilog in our frame. Please note that even simple class descriptions can get difficult to read. That's why UML diagrams were invented to better deal with classes, especially if you have multiple classes with complex dependencies between them. UML stands for Universal Modeling Language, and as you see, it condenses contents of a typical class. If you go through any OOP book or if you view our webinar, you will learn the first thing about class, that it combines pieces of data which are called properties, and now we have highlighted them both in the code and in UML diagram, and methods, which means tasks and functions that operate on those pieces of data. So now we have highlighted in red our methods. So this particular concept is called encapsulation, and it's very simple but convenient example of encapsulation using OOP. The other important concept is called inheritance. So now we've got the same class, but this time it's squeezed inside a SystemVerilog package called OOP. And as you see, below our original base counter class, we've got new class called load counter. And again, we are still in a relatively simple area, but it can get a little bit confusing for beginners. So we've got matching UML diagram. So as you see, we've got arrow going up from our load counter, our second class, and listing one new item, namely load method. And everything is okay here because we inherited all contents of base counter class inside load counter and just added new method called load. So this particular case is case of extending existing class by inheriting everything that it contains and adding something new to it. The other option could be, of course, modifying original contents of the parent class. Of course, you should go to our website and watch OOP webinar if you need more examples and more detailed explanations. Okay, let's jump to TLM, transaction level modeling. Basically speaking, transaction level descriptions represent higher level of abstractions, especially when compared to RTL known from synthesizable code. And they still contain components, they just work slightly different way. First of all, whenever any data transfer happens, of course, we've got producers and consumers of data, and the actual data transfer happens via transactions instead of signal changes. Something new that does not happen in RTL designs is the concept of control flow. So we can have data flow from point A to B or from B to A, but we also have the idea of who initiates and who executes transaction. And initiator is equivalent of something commonly called master, and executor is typically equivalent of commonly known slave block. If you want to create TLM diagram showing data flow, then of course you will be using typical arrows to present direction of data flow. But you must have some ways of representing control flow, and in TLM it is done via special port shape. A transaction initiator always has square-shaped ports. In our presentation we are adding green color to enhance differences. Transaction executor usually has circle-shaped export. And again, we are enhancing difference by making it red. Please note that it may be highly confusing especially for beginners, because export actually can be called differently. Long story short, sometimes it's explicitly called export, sometimes it's called implementation port, which is shortened either to imp or import. So again, it's very confusing that import is the form of export, but please remember, if you see import, it really means implementation port, not import. So again, if it's circular, it's definitely executor, and whether you call it export or imp really doesn't matter. So those two kinds of ports always are connected one-to-one. So one port to one export, no branching here. But there are some components, usually those that process critical data, that need to send the data to multiple recipients. For instance, multiple components that analyze data and make decisions whether verification is successful or not. So there is special port serving this particular purpose called analysis port. And as you see, it is diamond shaped, and we are using blue color to enhance differences. Please remember that analysis port is the only one that allows one-to-many connections. And it's very simple and very convenient that it has very simple functionality. That port has just one method called write that is called from within component that has analysis port, and implementation for that method is provided in components that connect to that analysis port. So basically speaking, our component that has analysis port just creates transactions, uses write to push them through that port, and then any component, any subscriber that reads data creates its own version of write procedure that extracts whatever is needed. So let's have a quick look at sample TLM diagram showing most typical elements you may encounter in TLM descriptions. First, we've got producer of data. And if producer is also initiator, we typically call it put producer. And again, since we see port attached to this producer, it's definitely put producer or initiator producer. And when we send data, in this case, it ends up in FIFO that contains two exports. So quick reminder, it means that FIFOs in TLM are typically universal executors. So no matter if they are sending or receiving data, they are doing it by request of other components that connect to FIFOs. And of course, you can guess that on the other end of FIFO, we must have our consumer. And this time, consumer is initiator, so we can call it get consumer. And as you see, it also has our diamond-shaped port, which means it is analysis port. And whenever a write method inside that port is called, anybody who is connected to that analysis port, in this case, we've got two subscribers that do so. Those subscribers have their own write method implementations that properly handle data sent by the consumer. Please note, because it may be confusing if you have never worked with TLM, analysis port exists and component calls that write, but it really doesn't matter if anything is connected to that port. That write call happens if there is somebody who implements write and does something with the data. That's okay. If there's nobody, it's still okay. And as you can guess, we do not have enough time to go any further, any deeper into TLM, so you have to watch our TLM webinar for more examples and explanations. And now we have to proceed to the interesting area of SystemVerilog interfaces, which can be called universal signal containers. First, you've got that main bright blue area, which groups a couple of signals: clock, reset, enable, data in, data out, ready, and a couple of attachments. which specify what are the directions of those signals. So we can say that SystemVerilog interface is a module-level container for signal and port direction data. What's beyond our scope is that it can also contain behavioral code, for instance, tasks that describe write and read or similar procedures, assertions that verify protocols, etc., etc. Example of code that matches interface that we have seen in the diagram at the top is now showing up in our slide. And as you see, we've got main area that declares signal by name and size. So that's our bluish area in the diagram. And then we've got mod ports. Those are the attachments that specify directions. Please know that we repeat signals that belong to the interface in mod port descriptions, adding input, output, and other standard SystemVerilog directions here. What you absolutely have to remember is that mod ports present directions as seen from the module that connects to the interface. So if we see that in slave the out is output, it means that it is output from the point of view of the slave block connected via slave mod port, not from the point of view of the interface itself. Okay, something very, very important, because vast majority of people who are giving up on UVM are stopping precisely at this location, virtual interfaces. First thing that you have to remember, especially if you have not worked with classes in SystemVerilog before, while you can have classes instantiated inside modules, reverse statement is not true. So it means that inside classes you cannot have modules or anything module-like, which of course includes SystemVerilog interface. So we've got dilemma: how to connect classes that produce data and have to send it to design under test with components, RTL level components that use interfaces. And of course, we've got that new concept called virtual interface. You may find various different sophisticated descriptions on virtual interfaces. From hardware designer's perspective, the best idea is to remember that virtual interface is just a pointer to real interface. And classes in all programming languages are always allowed to use various kinds of pointers. So it should be quite obvious that while you cannot have real interface inside the class, virtual interface or pointer to the interface should be absolutely legal. Please note that there is, of course, one important provision. Before you do anything with object that belongs to that class with virtual interface, you must tie that pointer to real interface because there are not many operations that can be performed on empty pointer here. It definitely has to be connected to a real interface. Of course, you can do that kind of connection in constructor, in new function that every single class must have. But it's okay when you deal with just plain classes in SystemVerilog. If you are dealing with UVM, you are not supposed to do it this way, because you've got something called UVM Factory and configuration database, which are responsible for tying virtual and real interfaces together. So please remember, virtual interfaces are the only area of UVM where TLM world meets RTL world. They are also one of the least popular SystemVerilog constructs because majority of hardware designers that do not do advanced verification may not even be aware that virtual interfaces exist. And of course, lack of understanding in this area is one of the main reasons of hostility towards UVM in hardware designers' world. Okay, so we have covered all the basics that we absolutely need here, and let's proceed finally to our UVM description. Let's present general overview of UVM. What you see in this diagram shows top-level module. It should be quite obvious that you cannot have very top-level class because you have to instantiate your design, and as we have mentioned earlier, you cannot instantiate module-like objects inside classes. So old-style module must be our top level, and inside we will have a couple of items. First, we will have our system bus, and it should not be surprised when I mentioned that it will be represented by instance of some SystemVerilog interface. And we will have instance of our design under test. Of course, it will be connected to the rest of the environment using our system bus or SystemVerilog interface. We will have UVM class-based verification environment, so it will be top level of the class part, and of course it will be talking to our system bus, and you can guess via virtual interfaces. And sometimes, not in all designs, typically ASICs will be without this block because ASIC has everything including clocks inside. In case of FPGAs, you may need the additional control logic blocks, typically handling clocks, resets, or similar global signals. So let's concentrate for a moment on the contents of our class-based verification environment. You will definitely need some data items. Basically speaking, those are smaller chunks and complete transactions or sequences that are needed inside. So they will be generated, transformed into signal changes, sent to design under test. Design under test will be responding via signal changes, and of course they will be translated back to transactions that can be compared, analyzed, etc., etc. To send data items to DOT, you will need sequencers and drivers. Sequencers are just engines that process data items. Drivers are example of transactors or bus functional models that are translating from transactions world into RTL. Monitors, very similar but work in opposite direction. They are translating from RTL to TLM. We also need scoreboards, mainly to analyze results. And of course, there are other elements, but they are not needed for our basic presentation. If you prefer more programmatic approach to UVM description, here it is. Please note, it is not complete description of all classes available in UVM. Of course, it is UML diagram, so the top element in each box represents class name, and the next sub-elements are properties and methods within those classes. Some classes that are mentioned here should be just mentioned, but some other classes require some highlights. So let's do it. First of all, at the very top of hierarchy that we see here is UVM object. So practically everything that you are writing in your UVM test bench will, one way or another, be connected via those arrows with UVM object. Some of those elements you write will be closely related. For instance, UVM sequence items and actual sequences, as you see, are pretty close to the object. Also pretty close are TLM-related elements such as ports that we have mentioned, namely export, port, and import. Then we have another core element, UVM component. As you see, it itself derives from UVM object, but it adds a lot of functionality. Basically speaking, anything that builds hierarchy of your class verification environment must be a child, one way or another, of UVM component. And again, we've got some children already represented in this diagram. Some of them, currently highlighted in that pinkish color, are precise matches of those elements that we have seen in previous diagrams. So we've got UVM driver, UVM monitor, UVM agent, UVM scoreboard, and UVM sequencer. So those are the verification components that sit relatively close to design under test. We also need some way of organizing our work, and here we have UVM environment and UVM test, two classes that are sitting closer to the top level of our verification environment. Okay. One very important word of advice. If you open UVM-related books, articles written by verification engineers, they always start at the very top level and then gradually and frequently, not completely, descend to lower levels. And I know from practical experience and from talking to many hardware designers, it's totally unclear way of describing UVM to hardware designers. So in this webinar, we are using totally reverse approach. We are starting at the bottom, as close as possible to design under test, and then we are proceeding higher. So first step in that case will be establishing interfaces. If your DUT already has interfaces, that's okay. Otherwise, you have to add them. Then, in class world, you have to create data items. So they will be packets, most basic chunks of data, and then sequences that combine them. Then you will need sequencer and driver to send data from your test suite to design under test. And you will also need monitor to observe responses coming from DUT. Please remember, it's a reminder, driver and monitor are transactors or BFMs, which means that they translate between TLM and RTL layers. Then, especially if you plan to reuse your code, it's a good idea to create agent. It usually does not bring new functionality, it just conveniently wraps up together sequencer, driver, and monitor. Sometimes it adds better parameterization for more convenient reuse. And of course, if you are just playing around, you may survive without result checkers. But if it's something that should be final and really good product, it should contain scoreboards, subscribers, or similar elements that are just analyzing results and making decision if verification was successful or not. And when all those lower level components are ready, you have to wrap them up in something that can be executed. And depending on the complexity of your circuit being tested, sometimes UVM environment will be enough. Sometimes, especially when you need several environments, you will also need tests to wrap everything together. And when you have those higher level containers, you can create top level module, instantiate that class container, instantiate your design under test, tie everything together, and run your test. Speaking about design under test, of course, typical synthesizable design is written at RTL level. Typical UVM test bench is written at TLM level. And as we have mentioned earlier, interfaces, SystemVerilog interfaces sit between those two worlds. Of course, if it's new SystemVerilog design, probably it is already using SystemVerilog interfaces, but what if it's older design or something written in different language? So what to do? Of course, you can create SystemVerilog wrapper that communicates to the outside via interface, but with your DUT using traditional RTL level. Please note it is especially important if you have some older Verilog code or let's say VHDL design that must be tested via UVM. Please note that in general, the less UVM test bench knows about design under test implementation details, the better it is. So it's yet another argument for using those wrappers. They simply discourage picking directly into the contents of the design under test. Okay, so now we have covered all background information. Let's analyze flow in a more graphical, animated way. So again, we will be using bottom-up approach, as we have mentioned earlier. And in the next couple of slides, first we will see non-class, traditional SystemVerilog elements, and then we will start adding class-based elements. So here's our first slide. As you see, we've got our top-level module, we've got our DUT with appropriate interface mod port specifying directions of all involved signals. Of course, it must be connected to SystemVerilog interface instance. And please note that it's one of those cases when SystemVerilog naming conventions are totally user-unfriendly. Because if you look carefully at this diagram, you've got something that is called in SystemVerilog interface, but it really looks more like a bus. And you've got something that looks like interface that connects bus with the module, with your design under test, but in SystemVerilog it is called mod port. So you have to live with it. I don't think it will ever be changed. Just remember that it's not the most intuitive part of SystemVerilog here. Then, as we have mentioned earlier, some control logic may be needed, especially in case of FPGA. So some always block generating clock, something generating resets, enables, or other global signals. And of course, you will need UVM class-based verification environment. Within that environment, typically we'll be starting by creating packet. That's the most basic chunk of data that lets you build sequences. Basically speaking, they are groups of packets that can be sent to your design under test. Once you have those sequences, you can build something that will be handling them. So, of course, you will need sequencer, that, again, is engine that processes sequence data, driver that translates sequence data from transaction level to RTL, and monitor that collects responses and translates it back to transaction level. Of course, that environment must be connected with the rest of our design, specifically with the bus. And as we can correctly guess from our previous discussions, virtual interfaces will be utilized here. Of course, driver needs virtual interface to be able to drive signals of the bus, which of course then go to design under test. And when design under test responds and drives some other lines of the bus, monitor detects those changes and creates some transactions that later can be compared with some patterns to verify if everything is okay or not. So what we see so far is relatively simple, and we could immediately start testing. We just have to tell top-level module how to execute stuff that is contained in our pinkish oval structure called environment. And the situation is very simple here. We just need some initial block in our top-level module, and in that block we have to call run test. Run test, in case of just one environment or one test present, will automatically pick it up. If you, in larger designs, have multiple environments, you can select name by specifying it as argument of run test. So that's something very essential, but as we have mentioned earlier, we can improve, especially improve reusability of our design by wrapping sequencer, driver, and monitor into an agent. Again, if you add a couple of parameters, reuse of agent is much easier than reuse of separate sequencers, drivers, and monitors. Another thing that we have also mentioned is adding scoreboards. As you see, they connect to analysis ports. The simple one that we see here just contains one export, so it connects to one analysis port, but of course we can have more complicated scoreboards that connect to multiple analysis ports and do quite advanced comparisons. Please remember that if you are coming from hardware design world, probably you would expect that scoreboard will be sitting inside agent. But please remember, in class environment, you can connect any component with any other component as long as they have matching ports. So, of course, scoreboard could be inside agent, but it's not necessary, especially in case of advanced scoreboards that compare data coming from multiple sources. It will be very normal to keep them at relatively high level. Okay, so now we finally see all typical elements of environment built using UVM, test environment built using UVM. But please note that we can get more complex designs. So right now, as you see, we've got one subtle change. We renamed our agent master agent, which means that it is quite common to have multiple agents dealing with special areas that need to be tested in our environment. So multiple agents, quite common. Please note that multiple environments will also be quite common. You can survive with one environment, but there are obvious reasons to add another environment. Typical example, if your design under test has multiple interfaces, for instance, if it's some design that translates from, let's say, serial to parallel protocol or vice versa, it would be quite common to have environment number one dealing with one protocol and environment number two dealing with the other. So multiple environments will be absolutely okay. Then you will need something to wrap them together, so UVM test will be a very good thing. And if you want to test different scenarios in your design, you can even have multiple tests. So now you have pretty practical overview of all options that can happen in even most complex designs. What we have mentioned and what is difficult to present on any diagram is UVM Factory. If you worked, let's say, with C++, you probably heard about this design pattern. Basically speaking, if you work with class-based and object-oriented languages, you can do something that is totally impossible in hardware description languages. You can create environment with components that can be created and replaced dynamically. So in VHDL or Verilog, you have to compile your blocks. Then they are elaborated, which means that before simulation starts, all connections are established. And when simulation starts, nothing can be changed. Only data flows between those components. In UVM, especially when you're using factory, at any moment when you decide that some component must be replaced, it can happen. And UVM Factory is the facility that lets you do those dynamic replacements. How it works. Basically speaking, UVM Factory lets you register object types while you write test benches. So you cannot invent new type of object. You just register whatever you can imagine may be needed. And then as simulation proceeds, at any time you can add new object or you can replace one object with some similar but representing different functionality that better suits the following tests. And please remember, it can happen at any time, not at the beginning of simulation, not only at the beginning of simulation. You can also register data fields of objects. That concept is known as knobs, and you can guess why that name was selected. Most typically, you are using knobs to fine-tune parameters of your verification components. So for instance, if you need sequence, you can have parameter that represents number of packets that will be generated, and it may be added as a knob that can be adjusted when you add new sequences. So long story short, if you have UVM Factory and configuration database that registers everything, then it gives you tremendous flexibility, definitely not allowed in RTL code. So now we should know all basic facts about the structure of UVM test bench. Let's proceed to actual running of the test bench. And as you see, there is concept of UVM phases. So when you run simulation of a test environment that contains UVM, it will be going through those phases that we list on the right-hand side. And as you see, names are pretty much self-explanatory. So let's just highlight those that are really, really important and most frequently used. First of all, you have run phase, which sits right in the middle. And you can create in your own components tasks that will be executed whenever run phase was entered. For all other phases, which are non-time consuming, you cannot use tasks, but instead you can create functions that again will be called whenever given phase is entered by your simulation. If we start in chronological order, functions for build and connect phases are definitely frequently written by UVM programmers, because when you build structure of your test bench, you definitely want to create new components and connect them properly. And again, it happens in those functions. And of course, phase called run is definitely critical, because if your test is supposed to do something, it will be mainly doing it in run tasks. So again, build, connect, run are staple subroutines that you will be creating. Something less frequently seen but still useful is report phase function. So if you create function called report phase, let's say in your monitor or scoreboard, you will be able to write something to standard output at the end of simulation when all data was collected and properly processed. Okay, we are entering the last stage of our presentation when we actually see code. So again, to match our suggestion presented earlier, we start at the lowest level, namely packet. Packet, as you see, inherits from UVM sequence item. That's the lowest level that UVM coders should use to represent data. And you can create multiple properties, as many as you need. If you need anything to be randomized automatically, of course, you have to qualify it with rand keyword. So in our case, packet data integer field is randomized. Last item integer field is not randomized. Then we've got object registration with UVM Factory. So if something directly inherits from object, it can be registered using UVM object utils. If it directly inherits from components, it will be UVM component utils. If you want to match registration of the object in the factory with knob registration, it can be done exactly as you see it here. So our packet data field can be registered as a knob. Again, if you use any random fields, of course, specifying constraints will be a good idea. This constraint restricts originally integer field to something that represents just 8-bit data. So that's it, relatively simple thing. Once you have packet, which is basic data item, you can build sequence out of it. And please note that in that case, you create your own sequence class based on UVM sequence. UVM sequence is actually a template, so you have to specify what specific data item will be combined into sequence. So, of course, in this case, we are combining packets into sequences. Then, of course, you are doing registration of knobs. In our case, integer field number of packets can be registered as a knob. Then you need body task. Body task is describing specifically how individual packets are created and how they are tied together to form the entire sequence. So the most important part here is the use of UVM do macro. That macro is the most convenient and fastest way of getting your packets created, because UVM do creates packet, randomizes packet, and fully synchronizes transfer from sequencer that processes sequence and driver. So we can say that UVM do handles item creation, randomization, and sending. Sometimes it would be too much. For instance, if you want to resend some packet or manually create contents of that packet, you need something simpler, and as you see, you do have UVM send. UVM send is skipping creation and randomization phase, so you can just create manually and set data fields manually, and then UVM send will do all the rest, actual transfer from sequencer to the driver. Of course, we also have some UVM info macros. As you can guess, they are printing informative messages to the console, so you can see what was happening during simulation. Next step is creation of the driver. As you see at the beginning, we are, of course, extending UVM driver class to create our own driver. And as we should remember from previous diagrams, UVM driver and our driver is, of course, our transactor that has to talk to interfaces. So we need our virtual interfaces here. And just to avoid situation when accidentally we've got driver, but it's not connected anywhere, in the build phase function, of course, it will be called when hierarchy of our environment is built, we can add those precautions. So basically speaking, we are checking in configuration database if virtual interfaces of our driver are connected with any real driver, and if not, we are getting appropriate error messages. In the driver, the most critical part is actually run phase task, because it says how driver is supposed to process our sequences. So as you see, the first part is calling getNextItem method that sits in the port of our driver. And basically speaking, it grants permission to the sequencer to send packet and wait till the sequencer is done with sending that packet. Once sequencer sent us packet, of course, we can retrieve data from that packet and synchronize it with our bus. So typically we will be waiting till resets or other global signals prevent us from doing anything. We will be waiting for proper edges of clock. And when it happens, we will be sending data from our packet received from sequencer to appropriate lines of our interface. At the end, we have to signal to the sequencer that we are done with this particular data item via item done method call. And of course, it gives sequencer permission to proceed to the next item. Everything that we have mentioned here typically happens within forever loop, because driver is busy bee that constantly waits for new chunks of data and is ready to send them to the interface. Next important part is monitor. As you see, it extends UVM monitor. Again, it needs virtual interface, and it also needs analysis port, because sooner or later some scoreboard will be connected to it. It also needs the same safeguard again against unconnected virtual interfaces that we have seen in the driver. So that's relatively simple part. Then we need run phase. Here we see our first example of dynamically creating a packet of data using a factory. So that line packet type ID create is typical way of requesting creation via factory. Then we've got our forever loop. Of course, that loop synchronizes with changes in our interface, of course, via virtual interface. So when we see that data is ready and when proper edge of clock was detected, we can do one optional thing, but still very important. We can mark beginning of transaction. UVM can register transactions for us, but only in case of sequences. It knows when transaction starts, when it ends. When transactions are detected by monitor, you definitely have to tell system when transaction starts, when transaction ends. So here's the way of telling system that here our new transaction begins. Then, of course, we read data from the interface and combine it into proper package fields. And when everything is ready here, we are calling write method of our analysis port. So if anybody is connected to that port, that particular component will be able to process that data. And again, when we reached a point of time, of simulation time, when the transaction should officially be ended, we can call endTR. And again, if you work in very simple environment, you will be able to see contents of the database in the text format. If you work in a simulator that was adjusted to the needs of UVM, for instance in Riviera, you will be able to see transaction data in internal features such as a waveform. Please note that here we see our use of report phase. So that function simply at the end of the entire process, when simulation already ended, will print information how many packets were received by a monitor, because as you see, every time new packet is received, we increment packet count variable. And we are getting very close. We can build environment now. So, of course, we are extending UVM env class. Please note that in most typical test benches, you don't have to create your own sequencer. You can use stock sequencer. So in this particular case, UVM sequencer clearly marked as the one using packet data type. Of course, we need instances of sequence, driver, and monitor. And please note that in case of sequencer, which is stock sequencer and does not require any configuration, you don't have to do it this way, but you definitely are allowed to directly create a sequencer in constructor of environment using its own constructor. But you can also do additional tricks here. For instance, you can use UVM top enable print topology variable that sits in the inside your environment. In this case, if you enable printing topology at the beginning of simulation, you will get nice printout of all classes and dependencies between them as you created them. So if you are not sure what you are doing, it can be very helpful debugging tool. In build phase function, we are using factory to build components. So here you can see the way that can be used to build monitor, driver, and sequence instance using factory resources. And then in connect phase, we have to connect our sequencer with driver. You should remember that in our diagram, it was the only transaction level connection that was visible. If you want to do connection, you always call connect method that sees in the port, in the initiator port, with argument specifying appropriate export that should be connected to that port. Of course, you still need run phase, and here most critical element, because it was relatively recently introduced to UVM. If you do not raise objections in your environment, then immediately after starting simulation it will end, because the processor, task processor of UVM looks at the objections, and if there are no objections raised, it immediately ends simulation. So first you raise objections, then given number of time you start your sequence by specifying on which sequencer it should run, and then when you are really done, so when all sequences were processed and all messages were displayed, you drop objections as you see in that last callout. And finally, top level. You see larger and smaller font. Smaller font means just plain SystemVerilog. Larger font means our UVM stuff. So you definitely need to attach proper library headers and packages. You have to create real interface instance. You have to instantiate your environment class, and of course your UUT. Then you can connect virtual and real interface using configuration database call. You can adjust your knobs. So in this particular case, you are overriding default value of number of sequences in the environment. And after those overrides, you can actually create that test and run it. So that's our run test task call. Again, if you had multiple tests, you could call them by name here. And that's it. Please know that before you jump into UVM, you should prepare your work and organize it so it's easier to you. Here's a handful of suggestions. First, create test package that will contain all UVM test class descriptions. So, for instance, it will contain all your drivers, monitors, etc. Inside that packet, import UVM PKG package and UVM macros header so that all subsequent files will see it. Then include all UVM test component sources. So after those headers, include your sources for drivers, monitors, etc. Then include DUT sources and test package in the header of your top-level module description. Import UVM PKG package and UVM macros header inside top-level module description. And then you don't have to worry about anything during compilation, because in the compilation line you just specify top level, everything else will be included in correct order. Of course, you still have to worry about specifying proper options. So that's it. You are ready to go. A few remarks related directly to Riviera-PRO. Alde Simulator provides most recent and some archival versions of UVM library tailored to better use simulator features. Two are worth mentioning. If you specify plus UVM Alde recording and plus UVM set recording detail as command line switches in simulator, then you will be able to see transactions in the waveform. And here's the example. And if you make any changes in your code, and if you are using Riviera's HDL editor, you have access to templates, very convenient templates that show you how to use virtually all UVM classes. So it's definitely worth remembering. So we are almost there. Please remember that UVM is like Halloween ghost. It may be scary at the very beginning, but as you get used to it, you are okay with it, and you realize that you are never in real danger. UVM can be very useful, especially when quick results are needed. UVM promotes interoperability and reuse, so initial work will be needed, but as you progress, you will be working less and less. Experienced users may notice that in some specific applications, solutions written from scratch is better than one offered by UVM. And again, it's in specific cases, in majority of cases, UVM will do good work for you. If you need more information, more training, check our website for trainings and other resources. And that's it. Please remember that in addition to usual PDF that is always available after session ends, this time we will add zipped up sample design that was used in our slides, so you will actually be able to see and even work with that design on your own Riviera installation or any other simulator installation. That's it. Christina, back to you.
Thank you, Jerry. It looks like we do have a few questions for you here. First question, I have seen both subscriber and scoreboard mentioned in the diagrams. Are they the same components in UVM?
They are not the same. If you open PDF later and look at the diagram, they are slightly different components. Long story short, subscriber is more simplistic. It already contains proper port which implements write method. So you have to work less, but it does not provide any special functionality. Usually, if you just need one port connection, it's very convenient. But if you need more advanced analysis, so if you have to compare transactions coming from different sources, the scoreboard will be more convenient. So, long story short, subscriber is very simplistic. One scoreboard is more flexible.
Okay, somebody mentioned virtual sequencer to me. Is that something different?
I think that the question is if there are differences between virtual and real sequencer that we have mentioned. Yes, there is a very important difference. Sequencers that we have mentioned are real sequencers that are doing work in very specific situation. Virtual sequencer is a higher level, quite abstract entity that is synchronizing multiple sequencers. So let's say that we have multiple environments with their own sequencers in our test, and definitely we want to be sure that they work in proper order, so there are no conflicts. In that case, we create virtual sequencer that is not handling any sequences. It's just synchronizing work of those other sequencers.
And the last few questions, everyone seems to be curious to get some more information about the main differences between OVM and UVM.
Basically speaking, UVM is newer and implements slightly better methods of doing verification. If you are working at the very, very low level, if you are not creating your own verification IP, those differences should not be that painful. Probably the most important difference is the one I have already mentioned, raising objections. So the most typical problem that people transferring from OVM to UVM encounter is that the simulation runs in 0 time and produces no result. So that's because there was no objection mechanism in OVM. You are just explicitly stating that you want to run test, and when it completed, that was the end of simulation. So long story short, the main differences happen at the synchronization level. So from point of view of individual sequencers, drivers, monitors, differences are not that critical. The higher you go, the more differences you will be seeing. The first release of UVM was very close to OVM, and now those differences are getting more and more visible.
Okay, thank you very much, Jerry. And this brings us to the end of today's webinar. To learn more about Alde solutions, we invite you to visit our website at aldec.com. Thanks for joining.